Okay, let's have a look at this slightly harder example on differentiation. We're given a curve. It's got a turning point at P and Q, and then it heads to the axis as an asymptote. In part A, we've got to show that the x-coordinates of the point P and the point Q are solutions of the equation tan 2x is equal to root 2. Well, to find any turning points, we need to differentiate the curve and then put that differential equation to 0 and find out what the solutions are. Now, our function here is a mixture of two functions. We've got sine 2x on the top and we've got e to a power on the bottom. It's an opportunity for us to use the quotient rule. Now, in a previous tutorial, I proved the product rule, which is here at the top, and a similar proof can be used to produce this slightly more complex equation of the quotient rule. Now, the quotient rule deals with a function that you can split into a function in the numerator, which we're going to call u, and a function in the denominator, which we're going to call v, both of which you can see we're going to have to differentiate separately, though. So let's get that out of the way first. Okay, the differentials, du dx, well, the 4 can remain there. The differential of sine 2x will be cos 2x. But remember, we have to differentiate, because of the chain rule, we have to differentiate 2x, and the differential of 2x is 2. So there is a multiplied by 2 in the front there. So that becomes 8 cos 2x. Now, to differentiate v here, we're going to have to use the chain rule again, this time substituting t for root 2x minus 1 and finding dt dx and dy dt. If you don't get that, look back at a previous tutorial where I discuss the chain rule. So using that chain rule, dv dx is equal to, well, it's the same thing, e to the root 2x minus 1, then multiplied by the differential of this guy, which is root 2. So we now have got the constituent parts of the quotient rule, and we need to stick it all together. So I can say that f prime x is equal to v, which is e to the root 2x minus 1, multiplied by du dx, which is 8 cos 2x. So I'm going to put the 8 there and cos 2x there. So that's my first term. Take away u, which is 4 sine 2x, multiplied by dv dx, which is root 2 e to the root 2x minus 1, and this is all divided by v squared. V is this guy here, so squaring it will be e to the root 2x minus 1 squared. Now, before we go on, we've got to do some simplification. Do notice that we've got an e to the 2x minus 1 and another e to the 2x minus 1 in the numerator, and that will cancel with one of the e to the 2x minus 1s on the bottom. So this is equal to 8 cos 2x minus 4 root 2 sine 2x, and that's divided by just one of these guys now, which is e to the root 2x minus 1, and that's f prime x. And to find the turning points, we have to set that equal to 0 and work out possible solutions. So I'm going to clear the decks and do just that. So we can multiply both sides of this equation by e to the root 2x minus 1, and that produces that the numerator here, 8 cos 2x minus 4 root 2 sine 2x, is equal to 0. And I'm just going to put those on opposite sides of the equation just so that it makes a little bit more sense. So I get 8 cos 2x is equal to 4 root 2 sine 2x. I notice straight away that the 4 will cancel with the 8, to give 2. And we're heading towards a tan function. The tan function is sine divided by cos. So if I make this the master side and divide through by cos 2x, I get that this is root 2 tan 2x is equal to 2. So moving things round again, I get that tan 2x is equal to 2 divided by the root of 2, which is equal itself to the root of 2, because 2 can be expressed as root 2 times root 2. And we've proved that the turning points are the solutions of the equation they have suggested in part A. So part B now effectively asks us to solve the equation and find the x-coordinate of the minimum turning point on the curve with equations. So they want the coordinates of point Q. Okay, let's clear the decks and have a go at that. I think the first point to recognise straight away is that our values for x are between 0 and pi radians. And because we've got tan 2x here, I'm going to say let big X equal to little x, and work out the solutions accordingly. We're going to need a cast diagram and work out the first solution, which is tan big X is equal to the root of 2. And I get from a calculator in radians, I get that x is equal to 0.955 ... So that's somewhere that is x in that quadrant. The next one will be in quadrant 3, where this angle will be pi plus 0.955. So our list of solutions are that x is equal to 0.955, and our next solution is pi plus 0.955, and the next one, if we need it, is 2 pi plus 0.955. Remember, these are solutions for big X. Little x will be half these amounts. So these are our first two solutions. This must be coordinate P, and this must be coordinate Q. And if you put that into a calculator, this is the coordinate of Q. X is equal to 2.0484. But they've been slightly tricky. This is the coordinate of Q of fx. We want the coordinate of f2x. And you should know that when we multiply the x value within a function, the curve concertinas in by a factor of 2. So the x-coordinate of f2x will be our original value, which is 2.0484 divided by 2, which is equal to 1.024, and that is 23 dp. And that is your first answer. In part 2, they now need the minimum point of this curve. Now, what they've done is they've taken fx and they've turned it upside down by this negative sign. So they now want this solution. And if you notice, it's not f2x anymore, it's fx. So we can take this original curve. So let's have a look at what they've done to the curve. Yes, we've already established they've turned it upside down by this negative sign. Then they've multiplied it by 2, which doesn't affect the x-coordinate. And then they've raised it in the air by 3. Again, that does not affect the x-coordinate of the turning point. So the answer will be simply this guy here. What used to be a maximum, you see, has turned into a minimum by the fact that they've multiplied the curve by -1. Multiplying by 2 doesn't move the curve horizontally, nor does adding 3 to it. So I can say the min point of y is equal to 3 minus 2 fx And that's going to be equal to our first solution. So this is x min is equal to our solution here, which I'm going to quote to 3 decimal places, which is 0.478 and 3 dp, as I said. And that you'll find is the answer to the second part of part B. So a question that involves both the quotient rule for differentiation and then finding trig solutions and then transformations of curves. That covers quite a lot of the syllabus. I hope you followed that okay.